Imagine a pair of particles so deeply connected that the state of one instantly determines the state of the other, no matter the distance between them. This phenomenon, known as quantum entanglement, defies our classical understanding of space and time, earning it the eerie nickname spooky action at a distance. But wait, we're not done talking yet. Quantum entanglement occurs when particles such as electrons or photons become linked, and the state of one particle instantaneously determines the state of the other, regardless of the distance between them. This means that if you measure the spin, position, or polarization of one entangled particle, you immediately know the corresponding property of its partner, no matter how far apart they are. This instantaneous connection defies our classical understanding of space and time. The concept of entanglement was first introduced in the early 20th century as part of the development of quantum mechanics. In 1935, Einstein, along with physicists Boris Podolsky and Nathan Rosen, published a paper challenging the completeness of quantum mechanics using what is now known as the EPR paradox. They argued that if quantum mechanics were correct, it would imply that entangled particles could instantaneously affect each other, which seemed impossible and violated the principle of locality, which states that objects are only directly influenced by their immediate surroundings. Despite Einstein's reservations, numerous experiments over the decades have confirmed the reality of quantum entanglement. One of the most famous experiments was conducted by physicist Elaine Aspect in the 1980s. Aspect and his team used entangled photons and demonstrated that the measurement of one photon instantaneously affected the state of the other, even when separated by significant distances. This experiment, and others like it, showed that the predictions of quantum mechanics held true and that entanglement was a real phenomenon.
How do entangled particles communicate? In truth, they don't communicate in any classical sense. When two particles become entangled, their properties become so deeply linked that the state of one instantly influences the state of the other. This connection is a fundamental aspect of quantum mechanics, rather than a transmission of information. Imagine two perfectly synchronized clocks. Changing the time on one instantly changes the time on the other, without any signal being sent between them. This synchronization is an inherent property of the entangled particles. The implications of quantum entanglement are profound and far-reaching. One of the most exciting potential applications is in the field of quantum communication. Because entangled particles remain connected regardless of distance, they can be used to create a secure communication channel that is immune to eavesdropping. This is possible through a process called quantum key distribution (QKD), which uses entangled particles to generate a shared, secret encryption key between two parties. Any attempt to intercept or measure the particles would disturb their entangled state, revealing the presence of an intruder. Quantum entanglement also plays a crucial role in the development of quantum computers. Unlike classical computers, which use bits to process information in a binary state 0 or 1, quantum computers use quantum bits, or qubits. Qubits can exist in a superposition of states, representing both 0 and 1 simultaneously. When entangled, qubits can perform complex calculations at unprecedented speeds, potentially solving problems that are currently intractable for classical computers. This capability could revolutionize fields such as cryptography, materials science, and drug discovery. Moreover, quantum entanglement challenges our understanding of reality itself. It suggests that the universe is not made up of isolated, independent particles, but rather a deeply interconnected web where everything influences everything else. This interconnectedness hints at a fundamental unity underlying the apparent separateness of objects in the universe. Despite its many fascinating implications, quantum entanglement also raises numerous questions and challenges. How can particles influence each other instantaneously across vast distances? What does this mean for our understanding of space and time? Physicists continue to explore these questions, seeking to develop a deeper understanding of the nature of reality. In conclusion, quantum entanglement is a mysterious and profoundly important phenomenon that has transformed our understanding of the universe. From its origins as a theoretical puzzle to its potential applications in quantum communication and computing, entanglement continues to push the boundaries of science and technology.